Independent events. Consider 52 playing cards and an experiment of drawing 2 cards for 2 events. Let E equals event that the card drawn is spade and F equals the event that the card drawn is an ace. Then probability of E equals 13 by 52, which is 1 by 4, and probability of F equals 4 by 52, which is equal to 1 by 13. Also, the event common for E and F is an ace of spade. Then probability of E intersection F equals 1 by 52. Hence, probability of E by F equals 1 by 52 divided by 1 by 13, which is equal to 1 by 4. That is, probability of E by F equals 1 by 4, which is also equal to probability of E. Similarly, probability of F by E also comes out to be equal to 1 by 13, and probability of F by E is also equal to probability of F. Prove that if E and F are independent events, then so are the events E and F dash. Solution: E and F are independent events since P of E intersection F equals P of E into P of F. Now from the Venn diagram, E intersection F and E intersection F dash are mutually exclusive events. Also, E equals E intersection F union E intersection F dash. Then probability of E equals probability of E intersection F plus probability of E intersection F dash. Therefore, on simplification, we find probability of E intersection F dash equals probability of E into probability of F dash. Therefore, E and F dash are also independent events. Important points. Two events E and F are said to be dependent if they are not independent. That is, if probability of E intersection F is not equal to probability of E into probability of F. Sometimes there is a confusion between independent events and mutually exclusive events. The term independent is defined in terms of probability of events, whereas mutually exclusive is defined in terms of events, that is, subset of sample space. Moreover, mutually exclusive events never have an outcome common, but independent events may have a common outcome. Clearly, independent and mutually exclusive do not have the same meaning. In other words, two independent events having non-zero probabilities of occurrence cannot be mutually exclusive, and conversely, that is, two mutually exclusive events having non-zero probabilities of occurrence cannot be independent. Two experiments are said to be independent if, for every pair of events E and F, where E is associated with the first experiment and F with the second experiment, the probability of the simultaneous occurrence of events E and F when the two experiments are performed is the product of probability of E and probability of F calculated separately on the basis of two experiments. That is, probability of E intersection F equals probability of E into probability of F. Three events A, B, C are said to be mutually independent if probability of E intersection F equals probability of E into probability of F, probability of E intersection G equals probability of E into probability of G, and probability of F intersection G equals probability of F into probability of G. And also probability of E intersection F intersection G equals probability of E into probability of F into probability of G. If at least one of the above is not true for the three given events, we say that the events are not independent. Example: a die is thrown. If E is the event that the number appearing is a multiple of 3 and F be the event that the number appearing is even, then find whether E and F are independent. Solution: the sample space is 1, 2, 3, 4, 5 and 6. E contains the elements 3, 6 and F contains 2, 4 and 6. So E intersection F contains only 6. Probability of E equals 2 by 6, that is equal to 1 by 3. Probability of F equals 3 by 6, that is equal to half. And probability of E intersection F equals 1 by 6. Clearly, probability of E intersection F is equal to probability of E into probability of F. Hence, E and F are independent events. Example: 3 coins are tossed simultaneously. Consider the event E that represents 3 heads or 3 tails, and F represents at least 2 heads, and G represents at most 2 heads. Of the pairs EF, EG and FG, which are independent and which are dependent? Solution: the sample space contains the shown elements. Similarly, E, F and G contains the shown elements. E intersection F contains H, H, H. E intersection G contains T, T, T. F intersection G contains H, H, T, H, T, H and T, H, H. Therefore, probability of E equals 2 by 8, which is 1 by 4. Probability of F equals 4 by 8 and probability of G equals 7 by 8. Probability of E intersection F is 1 by 8. Probability of E intersection G is also 1 by 8 and probability of F intersection G is 3 by 8. So, probability of E into probability of F equals 1 by 8. Probability of E into probability of G equals 7 by 32. Probability of F into probability of G is 7 by 16. Now we can clearly see that probability of E intersection F is equal to probability of E into probability of F, but the other two, that is probability of E intersection G and probability of F intersection G, are not equal to the product of the respective probabilities. Hence, the events E and F are independent while the events E and G and F and G are dependent. Example: in the 2 dice experiment, if A is the event of getting the sum of the numbers on the dice as 11 and B be the event of getting a number other than 5 on the first die, then find probability of A and B, and also find whether A and B are independent events. Solution: the total number of elementary events is 36. Number of elementary events favorable to A is 2, and that for B is 30. Therefore, probability of A is 1 by 18 and probability of B is 5 by 6. Probability of A intersection B, that is probability of getting the sum of numbers on dice as 11 when 5 does not occur on first die, is 1 by 36. Therefore, probability of A intersection B, which is 1 by 36, is not equal to 1 by 18 into 5 by 6. Hence, A and B are not independent events. Example: a box of oranges is inspected by examining 3 randomly selected oranges drawn without replacement. If all the 3 oranges are good, the box is approved for sale. Otherwise, it is rejected. Find the probability that a box containing 15 oranges, out of which 12 are good and 3 are bad ones, will be approved for sale. Solution: let A be the event of drawing a good orange in the first draw, B be the event of drawing a good orange in the second draw, and C be the event of drawing a good orange in the third draw. Then the required probability is probability of A intersection B intersection C. Now, since there are 15 oranges, out of which only 12 are good and 3 are bad, so probability of A is 12 by 15. Now, after event A, we are left with only 14 oranges, out of which 11 are good. Therefore, probability of B equals 11 by 14. Now, after event B, we are left out with only 13 oranges, out of which 10 are good. So, probability of C equals 10 by 13. Therefore, our required probability is equal to probability of A into probability of B into probability of C, which is equal to 44 by 91. Example: if A and B are 2 independent events, then the probability of occurrence of at least one of A and B is given by 1 minus probability of A dash into probability of B dash. Solution: probability of at least one of A and B is equal to probability of A union B, which is equal to probability of A plus probability of B minus probability of A intersection B. Now, probability of A intersection B can be written as probability of A into probability of B. Taking probability of B common, we get probability of A plus probability of B into 1 minus probability of A, which is equal to probability of A dash. Therefore, we get probability of A plus probability of B into probability of A dash, as you can see. Now, this is equal to 1 minus probability of A dash plus probability of B into probability of A dash, because probability of A is nothing but 1 minus probability of A dash. Now again, taking probability of A dash common from the last two terms, we are left with 1 minus probability of A dash into 1 minus probability of B. Now we can replace 1 minus probability of B with probability of B dash. Therefore, we get our required result, that is 1 minus probability of A dash into probability of B dash. Hence, it is proved. Example: events A and B are such that probability of A is half and probability of B is 7 by 12, and probability of not A not B equals 1 by 4. State whether A and B are independent. Solution: probability of not A or not B is 1 by 4, which is given. This implies probability of A dash union B dash is 1 by 4, which can be written as probability of A intersection B whole dash is 1 by 4. That is 1 minus probability of A intersection B is 1 by 4. Doing this, we get probability of A intersection B is equal to 3 by 4. Now clearly, probability of A intersection B is not equal to probability of A into probability of B. Hence, A and B are not independent events. Example: given that events A and B are such that probability of A is half, probability of A union B is 3 by 5, and probability of B is P. Now find P if they are number 1 mutually exclusive, number 2 independent events. Solution: number 1. If A and B are mutually exclusive events, then probability of A union B is equal to probability of A plus probability of B. So P is equal to 3 by 5 minus half, that is 1 by 10. Number 2. If A and B are independent events, then probability of A intersection B is equal to probability of A into probability of B, that is equal to half P. That implies probability of A plus probability of B minus probability of A intersection B is 3 by 5. So P comes out to be equal to 1 by 5.